We have already discussed the Bohr second postulate of quantization. As per this postulate, we have already described that angular momentum, that is Ln for the nth orbit, which is equal to m, mass of the electron, velocity of the electron in nth orbit, and the radius of the nth orbit, is the integral multiple of h by 2 pi. It states the quantization of the angular momentum and refers that the electrons moves in some specific stable orbits. De-Broglie explained the Bohr second postulate of quantization, and he argued that electron its circular orbit must be seen as the particle wave, which can lead to the standing waves under the resonance condition. That is, the total distance traveled by the wave is integral multiple of the wavelength. If electron is moving in a circular orbit, then in one revolution it covers the distance 2 pi Rn, where Rn is the radius of the nth orbit. And this distance covered by the electron is the integral multiple of the wavelength of the electron in nth orbit. As per the de Broglie concept, there is a wave associated with the moving particle and having a wavelength that is given by lambda equal to h by p or h by mv. This is called de Broglie wavelength associated with moving particles. Therefore, this implies that n into h by m into vn, velocity of the electron in the nth orbit. We bring this mvn on the left side, so it will come 2 pi mvnrn equal to n into h, and bring this 2 pi on the right hand side, we will have mvnrn equal to n into h by 2 pi. That is, the angular momentum is integral multiple of h by 2 pi. This is the quantum condition proposed by Bohr for angular momentum of electron. An electron in hydrogen-like atom is in excited state. It has a total energy of minus 3.4 electron volt. Total energy in say nth orbit is minus 3.4 electron volt. We have to find the kinetic energy. We know, which we have already discussed, that kinetic energy in nth orbit is the negative of the total energy in nth orbit, and potential energy in nth orbit is the twice of the total energy in the nth orbit. So kinetic energy, which is asked in the question, equal to minus of minus 3.4, that is equal to 3.4 electron volt. Second is de Broglie wavelength of the electron. The de Broglie wavelength with the electron, which is a moving particle, is given by lambda equal to h by p, and this p can be written as, because we know kinetic energy is p square by 2m from mechanics, so p will be equal to root 2mk. We replace this p, so we will have h by root 2mk. This k is the kinetic energy which electron have when accelerated from the potential v as having the charge E. So k will be equal to EV. Therefore, we replace this k equal to 2 into m into EV. And if we solve this, because h is the Planck's constant, its value is known, mass of the electron is also known, and charge on the electron is also known, we will have a relation that wavelength lambda is equal to 1.227 nanometer by root V. So using this formula, we will have 1.227 nanometer divided by root, and the potential to get the kinetic energy of 3.4 electron volt, it will be potential is 3.4 volt. So 3.4, and it will be approximately equal to 0.663 nanometer. Therefore, we have to remember that wavelength of the wave associated with the moving particle is 1.227 nanometer by root V, where V is the potential difference through which electron was accelerated to have the energy, kinetic energy as EV. Now, question number 2. Let an electron in the nth orbit of the hydrogen atom in Bohr model. The circumference of the orbit in terms of the De-Broglie wavelength of that electron is. It already we have discussed that circumference is given by 2 pi Rn for the nth orbit, and it is integral multiple of the wavelength of the wave associated with the moving particle. So circumference is n into lambda n. This is the answer.